Let's get started. So I have your exams. We can talk about it at the end of the class. Okay. Overall, I think most of you did pretty good, except always with some exceptions. But overall, I was satisfied. Is that what I'm looking for? Is what that you show me that you understand the material. The best thing to do that with me is to be neat and clear the way you present it, and that you follow the procedure. Okay. That journey will take you somewhere. All right. So that's really what I'm looking for. But obviously, you need to, even if you have the best handwriting and everything, you need to show me that you understand the material, no? Okay. So the procedure and everything there is to try to help you. So I only have one person stopping about the assignment that is due today. Okay. But basically, you see that I think every last time I showed you that to solve the equation of motion using MATLAB is not really that complicated. It's pretty simple, but what is hard is to find the correct equation of motion, no? Okay, so we're gonna keep doing the same thing. We have been doing equation of motion without damping. The other day, I introduced what was the equation of motion for the damping, and we did, remember the three cases. It was under damp, critically damp, and over damp. We kind of did I give you the equation and then I give you a handout with the closed form solutions. And I told you this is beautiful, but it's a lot of work and you can do something a lot faster just by using MATLAB and finding the numerical solution. Okay? So I'm going to do now to find the equation of motion of a damped system so I can give you another assignment of finding the equation of motions and probably to plot the numerical solution. All right, so all right, let's get started. So example. And the reason why I'm doing this example is because I was thinking about giving you a problem like this one on the exam. But then I was like, if we don't do at least something that is related on class, it might not be a good idea. So basically what I have here, this is difficult to plot for me. But basically, let's say we have two concentric circles that represent a pulley. So let's say you have a wire that comes on this side. Then on the inner one here, you're gonna have a spring connected to the ceiling or to a ground wall. And then let's say that the outside will be connected to a damper C. We know that the inner radius is R and the outer radius is R. Okay, so the question is, then I'm going to say that's the initial condition because we're going to do the so initial conditions will be x at t equals 0 and velocity, which is x dot at 0, we're going to say is also equal to 0. Okay, so the question here is to determine the equation of motion of the pulley system in function of x. Okay, so I mean, I haven't got it down, but if you want, we can do it up. So you want to define x as what? So x will be, you want to make it going up or down? Should not matter. Up, okay, so let's do it up. Okay, so let's say this will be x. Okay, all right. So, all right, so determine the equation of motion of the pulley system in function of x and uh, plot the solution for the following data. So you have some data, but then you're going to change two values randomly. You're going to tell me which one you want to use. So R equal to 0.8, let's say M equal to 20 kilograms. I, the moment of inertia, this is a disk, so it's M R squared divided by 2. And then just give me two values that you might consider for K and C. What do you want to use for K? The stiffness of the spring. The reason I'm doing this is so that we don't know if the system is critically damped, over damped, or under damped. No, it will be the surprise. So just say value for K, but 5, okay. Now say value for C, 6, okay. So that might be very damped, no? Looks like, okay. We need to put 50, we can play, no, later on. See if we can make different values. Okay, so part one is what? To find the equation of motion, no? So what is the first step? We do the dynamic. And this is, I think, the most difficult part of the whole problem. All right, so let's call maybe that middle point here O, just to help a little bit. Okay, so what will be the forces acting on this pulley system? I'm not gonna give the answer, so if you don't tell me, we're gonna spend how many minutes just looking at each other? Force of the spring. So let's assume that this is moving. You want to make assume that it's moving up or down or down. Okay, so if it's moving down, so maybe we should assume this moving down then. Okay, so what about if we assume this is moving up since it's up, okay? Okay, it should not matter, but so then the force of the spring should be what? It's ky, but we call it x, but you're right. Okay, but that's fine. That's very well. Now, what will happen to the damper? Okay. But this one, the force of the damper should be proportional to what? To the velocity, so Cx dot. What else do we have? Okay, tension, so here is, yeah, maybe, that was maybe it's assumed, so when it moves up, all right, so tension, no? And it would be easy if we assume everything is going down, no? Initially, so. Uh, is that it? Okay, you want to put gravity? We can put it, okay? We're going to put it in this case. But otherwise, what is the assumption you can do? is that you can say that initially this system is stretched, so gravity is not acting. Because if we put the gravity, we're going to get the equation. But then what's going to happen? We're going to get a constant, no? That's what we should get. Okay. Now, what type of motion is this pulley going to have? Okay, so we're going to have translations can be up and down. So let's say the mass of the pulley is m. So we can have mx double dot. And then what can we have? I sub O alpha, no? So I think this is the most difficult part, if you ask me. What should be step two? Okay, so Newton's equations. Okay, so since we have translation and rotation, we need to apply both of them. Now the summation of forces equals to MA. So this will give you what? Minus T minus KX minus CX dot minus MG equal to MX double dot. Okay, so I know we can rearrange it differently, but let's just leave it under this form. One. And then what is the second Newton equation we need to apply? Summation of moments equals to I alpha. What do we need to be careful about here? Okay, that we take the moments about the same point that we take the moment of inertia, no? Yeah? Same. Otherwise, it can be done different points, but you're going to get lost. All right? So don't do it. Let's keep it simple. Okay, so if we do this, then what do we have? What would be the moment created by the force T? Will be positive or negative? Positive, correct. What about mg? Okay, what about kx? Minus kxr. And what about cx? Okay, minus cx dot. So here, let me put r this way. That way we know what it is. And this should be 3r. Okay, so this will be our equation 2. Okay, so now what is the problem? What is that you see in your head? So we want to write everything in full. Equal to what? I forgot to put equal to I sub naught alpha, no? But we know that alpha, we can leave it as alpha if you want, but alpha is also theta double beta. No, alpha or theta double beta. So it's about. Okay, so you stop here. How many nodes do we have? We're gonna have T, X double dot, and yeah, what? No, because we want in function of X. So X double dot or X will be the same, no? And we have basically theta double dot if you want, or alpha. So basically 2 equations, 3 unknowns. What do we need to do? We need to find one additional equation, no? Okay? So here we go. So step 3, we find the additional equation. And generally, we say that we're going to get the additional equation from where? Either kinematics or geometry, no? Okay, so this one is a difficult part now. That's why I decided to do this problem. Let me call this point here, whatever, A. Okay. So now, what can be the third equation? So basically, maybe I did here a little mistake over here of notation. Not that much of notation, but what is the little mistake maybe that I've done over here? Let me know what is the little mistake that I've done. Actually, I told myself, and it's not for not paying attention. What is X? X is the motion of point O, no? So is this going to move X? It's not going to move X, no? It's going to move more than X, no? And this one, the same thing. So let's say that this one, let's say then this will be, this should be here, let's say this one, KX1, CX2, and this is the original X, no? So here we need to be careful. So this will be KX1, and this will be CX2. Do you understand here? Yeah, but since upper here X. We can change it again if you want, okay? But we would, yes, it would be easy probably to do it in function of theta because theta would be the same for all of them. I agree with you. But we will still have to find the relation between the x1 and theta. You understand? So it's not going to be less work. Okay? But yes, it would be more sense to be theta. But since it's x is x, no? Okay? So, all right, here we go. So now, how can we find? So let's see. This is x over here. This is what? X1. This is x2, no? That we call. Okay. So what could be the equations that we can write? We can maybe almost just do that by geometry, but what can we do? There's an easy way. There's one that's a bit more complicated using the equations. The one we talk about this morning. You can maybe find the velocities, no? Or what can we do? Okay, so let's do it maybe the complicated way so that maybe you have to understand it. So basically, what is the velocity of this point? I mean, is this point moving? No, so really zero. So really, I mean, again, I mean, I can do this very quick, or I can do this very long, but I don't know if I'm going to lose you on the understanding, no? So, not sure what you want me to do here. Okay, so let's do it maybe the complicated way, okay? All right, so from this point, I think it's for understanding. So basically what I'm trying to do is what? Velocity equal what? dRdt, no? So where R basically is the deformation. So we can determine R. So we have dr could be equal to what? V dt, which will mean that we can find the deformation by just integrating the velocity, no? Okay, so I know it's an easy way to do this. So VA equals 0. So what can we do now? We can calculate the velocity of point O. Then we can find the relation between omega and so on. So this will be VA plus omega cross R of O with respect to A. This is 0. Okay. Then what do we know? So then this is going to become what? IJK 0, 0 omega, which really omega, yeah, we can leave omega, it doesn't matter. What is the position of O with respect to A? R0, 0. So basically it's going to give us that V sub O will be equal to what? 0 and R omega, which kind of makes sense, no? And really this is equal to what? This is really our X, no? Yes, does that make sense? This is the point O, no? Okay, so from here you could write the equation X equal R omega, or you could say what? X equal to R. What is omega? Okay. Sorry, I should have put here, this is, sorry, so maybe, what is the mistake I've done here? This is X dot, no? So this is X dot equal R d theta dt. So this will mean what? X will be equal to the integral of R d theta dt dt, which would give you what? X equal R theta. Yes? Okay. So then we can decide what we do. Yes. No, VA is 0 because let's see, what is the velocity of this point here? Okay, so this is the same cable, no? So what's the velocity of this point? And the velocity of this point then? So if you look at it, this is like having a wheel, if you want, or pulley rolling on a surface, no? This pulley is rolling about this point, but this point is not moving. Does that answer your question or no? Okay, this is really from dynamics, 100%. This is what it was called in dynamics. A is an instantaneous center. Okay, I mean, we know this. Okay, we could have done that very quick. Okay, next. But again, I'm doing it the complicated way because I know at least we should not be error. So let's call this point here maybe B and this point over here C. So what will be VB? So to make it easy, we can say now VB will be equal to what? VA plus omega cross R of what? B with respect to A. What is still VA? 0. So we keep doing the same thing over and over, okay? So I, J, K, 0, 0. What is the position of B with respect to A? Oh, sorry, I'm going too fast. So this is omega. What is the position of B with respect to A? To R, 0, 0. So easy to see that over here what we're going to get is VB equal to what? 0 to R omega, no? Okay, and we follow the same procedure as before. This should be equal to what? This should be, this is for which point? This should be x dot sub 1, no? Okay, so basically we can solve here the same as before. From here we get 2r d theta dt equal to x dot 1. So we can say that x1 is equal to the integral of 2r d theta dt times dt. This cancel this one. So this will give you now that x1 is equal to what? 2r theta. Okay, so I'll do the complicated way and then I will give you the easy way, okay? That way you have both of them, but at least this one is. Okay, and now similarly, what can we do? Velocity of C, no? Will be equal to what? VA plus omega cross R of C with respect to A. So what is VA again? Is 0. So from here, we're going to get A, J, K, 0, 0, omega. What is the position of C with respect to A? Is it 4? Yeah, you're right. 1, 2. Yeah, because it's 3 plus 4. Yeah, thank you. So here was R, 2 R's. Yeah, it's 4. 4 R, 0, 0. So basically, this is going to give what? DC equal to 0 for R omega, and this should be equal to what? 0 x dot 2, no? Sorry for mixing the notation. Maybe I should have called 2C, okay? But once you understand, the notation is not a problem. Okay, so from here again, we can write what? 4R d theta dt equal to x dot 2. So we can find that. I mean, can I just skip this one? X2 will be equal to what? 4R theta, no? Okay. So, yeah, might be just easy to do it in function of theta, no? We have everything now. We run in function of x. Okay, so let's go to the next page. Okay, so recalling the relation, we have x equals r theta, x1 equals to 2 r theta, x2 equal to 4 r theta. Okay, so we could use, if we wanted to write everything in function of theta, that's what we would use, no? Okay, but now we need to do something different. So what do? We could say over here, using these three relations, we could write in function of theta. Theta would be equal to what? X over r, which will also be equal to what? X1 over 2r, which should be also be equal to what? X2 over 4r, no? Okay, so now what do we need to do? We need to find the relation, let's say, between x1 and x, no? So from this relation, we could say what? X1 would be equal to what? 2x, all right? And then from this one and this one, we could say what? X will be equal to, so x2 will be equal to what? 4x, no? Okay? Okay, so basically, x1 equal to x and x2 equal for x. This could be our equation. What do we have? So we should have 1, 2, this should be 3 and 4, no? Yeah? Okay. So this is, I think, long and derived, okay? Without too much questions, no? So let's say alternate way to determine equations 3 and 4. You're going to tell me it's a lot easier. I agree. But if you understand, so basically what could we do? What do you think I'm going to do? What could we use? We could use similar triangles, no? You have B, so CB, O, and A, no? Yeah, so what would be this? This will be X, this will be X1, this will be X2, no? Now, what would be those distances over here? I mean, you need to be careful with this one, but this will be what? From A to O, what do we say what? Was R, no? So this one is R, what would be the other one? I think this one should be 2R, no? And then what should be the last one? For R. And using similar triangles, you get to the same conclusion, no? Okay, so I agree this is a lot easier, but I don't know if it was gonna make sense or not. With the velocities, at least there is no confusion, agree? Okay, so if you do this, I'm fine with this as well, okay? Do you have any question about this? And then I say here using similar triangles. This will give you what? X over R will be equal to what? X1 over 2R will be equal to X2 over 4R, no? Which is exactly the same thing that we had over there. Any question? Yes.
Stupid one, but where do we get the distances for the radius between the points?
On the figure. Go step from here. I mean, point A is this point over here. So it's 3R plus the other R. Was that your question? Yes. So I think he answered it, no? Okay. No, I mean, that's why there's no silly questions, okay? Ask as much as you want. But I mean, I agree that I did all these equations that took about a page. You could have just done this, no? Which is fine with me. All right. I just want to make sure that I give you both options. Okay, so we did step 1, step 2, step 3. What we need to do now is the one to me that has no value. But we need to do it because we need to do it because we need to find the equation module. So what is step 4? Solve, no? Okay. So if you want, let's just recall all the equations that we have. We have minus t minus k x1 minus c x2 minus mg equal to mx double dot. And then we have t times r minus k x1 r minus c x dot 2 3r equal to I sub naught beta double dot. We have the equation x1 equal to x and x2 equal to 4x. Okay, this is the stage that personally I don't like to do. I go to Maple or MATLAB and I say just solve the system. No, even though in this case it's not complicated at all. So what are we going to do in this case? What can we do? We can substitute 3 and 4 into 1. No? And solve for t. No? Okay, so let's do that. So let's say substitute. So you want to do what? Substitute. Yeah, so you want to substitute in 2 and then replace. Okay, let's do that. So substitute 3 and 4 into. We're going to do the reverse, but it's fine. Yeah, it's 3. So you say replace 3 and 4 into 2. Is that what you want to do? I understand because you don't have the r. Yeah, it's fine. But then we're going to have to change that one into x, which is fine. Okay. All right. So basically what do we do here? We're going to have t times r minus, what was x1? So it should be minus 2k 2k yeah, xr, maybe put rx, I think would be more accurate, but since I put xr, tell me xr is fine. Minus what? What is x dot 2? So it would be 4 times 3, no? 12 c x dot r, okay? And this should be equal to what? I theta double dot. So let's try to do everything at once. I don't want to do too much. What do we know is theta in function of x? What is theta? It's x over r, no? Yes? Okay. So if you want, now we can say, and all right, so let's just rewrite this very quick. So let's just call this equation will be TR minus 2KRX minus 12 CRX dot will be equal to the I sub naught over R times X. Yeah, you're right. I just looking at that one. So let's put this one as well. Okay. All right, so now from solving equation 1 for For T, what do we get? T is going to be equal to minus kx1 minus cx2 minus mg minus mx double dot. So this will mean what? T is equal to what? I mean, this one is so simple, but it's still going to give us some algebra. What was x1? So it would be minus 2kx minus 3cx dot, no, 4cx dot minus mg minus mx dot. Finally, what do we do? Substitute t, let's say, into this equation here. Let's call it A. I mean, I should have done that with Maple, but okay, so what is that going to give us? That's going to give us minus 2kx minus 4cx dot minus mg minus mx double dot times r minus 2krx minus 12crx dot equal to I not over r x double dot. Okay, so let's see. This is going to give us what? That's just going to give us, let's divide all this side by r, okay? So it should give us what? I over naught r squared x double dot, no? So I keep this one this way. Now what's going to happen to this kx here? Remember, we have divided by r, so this one disappearing. So what do we get? So we're going to get here the minus 2kx minus 2kx, no? We get minus, we move him to the other side, so it will be plus 4k, okay, plus 4kx. What else? So will be, yeah, plus, I'm moving everything to the other side, so plus 16 CR, no, the R cancels out, no? 16 CX dot, sorry for that. Plus mg equal to 0. Oh, yeah, so this should be here. This then becomes m plus this one, no? Which don't make sense. Okay, so let me just rewrite this. This becomes m plus I sub naught over r squared x double dot plus 16 cx dot plus 4kx equal to minus mg. Okay, so what is the problem of us having mg at the beginning? What is the problem? Okay, or let me just write this. Or what should be this equation? It should be equal to x double dot plus I mean, let's leave it this way, okay? I don't want to complicate stuff, okay? What I'm trying to say is that at the end of the day, what is it we say? We say this should be of the form mx double dot, no? Plus the other two terms. So people, so the above equation is non-homogeneous, and in order to find the analytical solution, not needed for the numerical solution, a change in variable is required. So if you go back to your notes, what do we do for the change in variable? Remember we did one that we had a pendulum? Okay, what do we do? Correct. That's exactly what we need to do. So it's some x equilibrium here. Okay, so we're going to define here a new variable. What happened here? Does it need to be plus or minus? So I guess here's going to be, so let's see. We need to have x equilibrium needs to be negative. So we get mg minus mg. Okay, let me solve 1 second. Would be x would be x dot the new variable. X dot. Okay, let me look something here. This so. Okay, doesn't matter how we define it. Don't put any sign over here, okay? I will do it now. Okay, 5, where x EQ is x at equilibrium position. So what's going to happen at equilibrium? At equilibrium, there is no motion, no? Okay, let me put here. I mean, there's another way to do it, but I think this is the easiest way to do it. No motion. So what does that mean? What does that mean about the equation of motion? Let's call this one B. And equation B can be rewritten as what? 4kx equilibrium equal to minus mg, which this will give you what? X equilibrium equal to minus mg over 4K. Okay, so here put a plus sign. You will see what's going to happen. Okay, and x equal to x bar plus x equilibrium. We can write it as x equal to x bar minus mg over 4K. Okay, so if we have x now equal to x bar over 4K, what would be x dot? What should be x dot? Should be what? X bar dot, perfect. I mean, the notation is becoming crazy. And what should be x double dot? There should be the x, yeah, crazy notation. Smiley face almost, no? Or sad face. Okay. Again, I'll do a lot of detail, Jelly. So substituting into B, what are we gonna have? We're gonna have M plus I sub naught R square X double dot plus 16 C X dot plus 4KX equal to minus mg. So why are we doing this? You're gonna see, because then what do we have here? We have m plus I, so I naught over r squared. Crazy notation, sorry for that, would be x bar x double dot plus 16 c x bar dot plus 4k times what? No. X bar minus mj over k. And this will be equal to what? Minus mg. So now what's happening? Why did we do all this stuff? So you see that now this one will cancel with this one over here, no? This 4k. Yep. So basically at the end, we have m plus I sub naught over r square x double dot bar plus 16c x dot bar plus 4k x bar equal to 0. And now this time, this equation is homogeneous, no? Okay, so homogeneous. Okay, but we could have skip all these steps if we have made one assumption at the beginning of the problem. We talked about this before. Say that again. Correct, but then what is the assumption that we're making? that we are writing the equation of motion from the equilibrium position. Yes? You understand that part? Because if you say that you write it down from the equilibrium position, that means that you have the spring and the damper are already being stretched, no? And you write it from that location. Here we didn't mention it. You wanted to put mg. I say, okay, let's put mg, no? But what does that create? It creates that problem over here. That if you want to find the analytical solution, you first need to do this. Okay? Yeah, go. The what? No, but no. When you solve a non-homogeneous solution, generally you need to solve the homogeneous part plus the particular part. Okay, so it's twice the work. You see what I mean? So now that you have this under the homogeneous solution, I don't even know going to remember, but what should be the procedure? We assume a solution for x bar of the form d exponential of lambda x. Remember, we take the derivative, we substitute, and we do the law of algebra, no? Okay? But if we have to solve this numerically, we don't need to do anything else. Okay? So let's say this last step is not needed if initially it was stated to determine the equation of motion from the equilibrium position. Do you understand this? Basically, the only thing we need to do is same procedure. The only thing you will be removing is the mg, no? Okay, but if you want to do it, it's fine. But then if you put the mg, you're going to have to do this step at the end. I mean, if you want to find the analytical solution, if you want to find the numerical solution, we are completely fine. Okay? So let's go do the numerical solution, okay? And then I will tell you what would be the analytical solution. All right, so we need this equation. So okay, this is opening. I want to go back, maybe take the I want to discuss a couple of things. So let's see, ME400. Course material. Let's see, single degree of freedom. Don't leave now, because this is important. Then you can leave. But wait 2 minutes. Okay, so what I was trying to say before, okay, that I think some of you are shaking your heads, acknowledging, but probably, okay, so this is, remember we kind of did all this stuff the other day now with the critical damping, but what was the initial equation, the form of the initial equation? It was this one, and the right-hand side was equal to 0, okay? So in this case, we don't have m. What do we have? M plus I sub naught over R squared, no? But basically it's a constant. Oops, I don't know what I did. Then we don't have here C, but what do we have? I think it's 16 or 12, no? We don't have K, but 2K, no? But the process will be the same. In order to find the analytical solution to this problem, what do you need to do? Assume harmonic solution. Okay? You take the derivative, you substitute into the equation. You find the characteristic equation. Then you solve for the two roots and you substitute back into the assumed solution, no? That's what we did, okay? All right, and then depending on the damping, we did all this stuff. We didn't do it really. I just give you the handout. If you see all the pages, all the derivations, they are not fun. All those pages, we should have done all those pages, okay? I skip that. I think I give you this over here. We skip all this stuff, and I give you this handout, no? Summarizing all the result as well as the responses. And then we say, probably what's over here. Let's do this for, okay, we need to do that next. We'll do that later on. Okay, let's solve this numerically. Okay, so let's solve this numerically with MATLAB. File, open. I have to be careful here because share, all engineering share, ME400.
What was the I is I?
What was I sub not? That is the mass volume inertia of the pulley.
Yeah.
Oh, MR square over 2, I think we said. Yeah, I think I put it. Yeah, I put it on the data, MR square over 2. Okay, so ME400. So if you want, you can do the analytical solution. You're more than welcome. So spring, I think I moved the MATLAB from the semester, but let me move this one here, maybe new folder. And let's say pulley MATLAB, okay, just to, and try to use all files. So what were the files that were important the other day? Remember okay, so I guess I have here one called pulley. I don't know if that's the one for this program or not, but let's just copy it, okay? And then analytical, numerical, I have no idea. Let's copy this one numerical, okay? I don't know what I'm doing, okay? To tell the truth, but we need to modify those files. Copy. What is this? Spring 2024, pulley. Why didn't do the paste? Okay. All right, MATLAB, let's use DC1 pulley and numerical. Copy. Paste. Okay, so let's open here, file, open. What is the important one here that we need to find? To open, share, origin, share. ME400, Spring 2024, for the MATLAB, let's open this one. This is the important one. Okay, let's open the other one as well, but the other one should not be that important. Okay, so for this part, what do we have over here? We had, I think, 0 and 0, no? Okay, maybe 0 and 0 is not going to work, but let's see. So here is some data for, okay, we don't need this. I'm just going to put it here. So what do we have over here? What do we use for M?
20.
20. What do we use for K?
5.
5. What do we use for, 5. What do we use for C? I think it was 6, no? You told me, is that correct? 6. Then R, we didn't specify a value for R.
Yeah, we did 0.8.
0.8. You see that this is, I changed it already. This is MR squared, no? Did I put MR squared over 2? So this one, let's put MR squared over 2. Okay, so it is our problem. G equal 9.1, M plus I, this is 4K, and this one is 12, no?
Wait, further.
Because, yes, yeah, this one probably was in function of theta. So our M is what? Is M? No, this is what we have, no? I think that's what we have in our equation. Yeah, we have I sub O, I say what? MR squared.
Yeah, but up there, you have divided by R squared.
Yeah, and didn't is that what I specified? Okay. Correct. Thank you. So this is, and then we have for C, how much we had? 12? Oh, 16. Unless I'm wrong, 16, no? Yeah. From the equation of motion. If you want, we can put mg or not. So basically, we have all these values, and here you see that I'm putting, okay, I'm putting the mg over here, no? Yeah. So you see that if you do the numerical solution, you don't need to do the change of variable, no? You can just keep it over here. So we have minus c over m minus, what did I put here? Minus k over m, not k over c1 plus, okay, so let me just relook at the equation here, okay, for us. So this is our equation. So we need to rewrite x double dot. So this one will be negative, negative, negative. So three of them should be negative divided by the capital M, which is all this stuff. So minus C over M, minus K over M, minus mg over M. Okay, so this is DC function 1 pulley. DC function 1 pulley. Okay, so hopefully that will work. Okay, okay, so the data is not good at all. It's basically way overdone. No, it's going to 0, no? So I don't know, can we use different, I mean, just to play now, no? So maybe what can we do in order to make it play over here? To make it more better notation. So maybe let me increase this. I mean, the solution is here, is done. What happens is that the data we selected is not good. Let's see what would this give. Okay, so this one's a bit better. We're gonna see it's still, this one is also pretty dumb, no? So what about, I mean, we are just playing. What about we reduce the damping this time? 0. Then what do we get if we put 0? What are we gonna get? That's what we should get, no? Correct. Remember, it's staying at always the same oscillation, no? Yes. The damping should make this go down, no? But it's good. I mean, that's the way to learn, no? Okay. So let's put a small value. Okay. We are just playing with it. Let's just play whatever, 0.5. Okay. Again, I'm playing. Again, I don't have the correct. So that one's going to be good. You see, because this means what? That the amplitude is going to go down, no? So this data actually should look very good. This would be the case that we wanted to use, no? Okay, so you see that really numerically, how long did it take us? Probably 3-4 minutes, no, to find the solution. Yeah? Okay, instead of doing all the math. So basically, for the next assignment, what I'm going to do is assign you probably a couple of problems where you need to find the equation of motion, and I'm going to ask you to find the solution numerically. Okay? All right? All right. So let me give you back the example before I forget. Like I said before, I think overall I'm happy. It's always, few cases that are the exception, but so let's see. Oh, I know he's not here, so no. Okay, so who is this? I'm going to say the last 4 digits of your student ID. 7218. Here or not here? So what I put over here is use that you could easily get Okay? We'll do them all. Same thing for this person. Joshua, Napier. Same thing. I think with very little bit more. Same. And this one I say a little bit more, but even a little higher. 7012. About the same. I think with very little more, it should be able to get it plus. Ashak, Gina. 2709. We did it well. So 5398. 5398. You would let it more, you should be the 8. Shane, my question, please. Okay. Then 6034. 7212. Garrison Hoover. You know the marks. You know the marks. 6471. Right here. 7164. 6274. You deal with one problem. So 2676 and 1955. I think that's it, Bobby. Someone needs to make up. So let me do one thing because I did it last semester and I was pretty happy with it. The truth. Okay, let's do one thing. Okay, because some people did not do that good. I don't want to give them the perfect now. So for Thursday, I will create this stuff now. Okay. Working individual. You don't need to copy anything. I want you to redo the exam. I don't know it. But there is that condition. Is that I'm just going to go glance through it very quick. I'll be the one doing it. And basically, it's going to be that way. If it's perfect, means perfect presentation. And everything is perfect, I give you an extra 10%. If there's one little error or presentation or something, you don't get anything. Okay? You have plenty of time, no? I think everything we did here, I think with the first problem, I think we did it on the second or something. No? I mean, I want you to work individually. And I think the other two problems with time, you should be able to get them because they're not really that difficult. Okay? So for Thursday, perfection, presentation, and everything, double check, do whatever you want, but working individually, the goal here is that you learn the material, no? Okay? All right, see you Thursday then.